We want to welcome you to the Dallas Independent School District STEM Environmental Education Center virtual field trip. I want to say a very special welcome to Dallas Hybrid Prep and to Stephen Foster. Thank you for joining us on this beautiful, beautiful winter day. Teachers, if you're watching, you have not signed up, please do so. Go to www.tiny.cc/6-8 restoration and sign up for us. Please, we need a record of your attendance. The program today will be plate tectonics. During this virtual field trip, students will explore plate tectonics. Students will identify the major tectonic plates, describe how plate tectonics causes major geological events such as ocean basin formation, earthquakes, volcanic eruptions, and mountain building. Mr. Monroe will introduce you to plate tectonics. Ms. Ram will tell you all about ocean basin formation. Ms. Ramirez will cover earthquakes and volcanic eruptions. And Mr. Dominguez will tell you about the mountain building. Students, you cannot ask us a verbal question during this program, but you can go to www.tiny.cc/question-answer and fill out a question and send it in, and we'll be glad to answer that for you. Now I'm going to stop sharing my screen, and Mr. Monroe is going to tell you all about plate tectonics.
Good morning. Good afternoon, everyone. Boy, what a day. But listen, my little time that I have with you today on your virtual field trip today, we're going to start out by looking into a theory, what began as a theory called the theory of plate tectonics. Now, this theory was first proposed by Alfred Wagner. Now, this happened around 1910. Now, Wagner noticed that the shorelines of the continent seemed to fit together like a giant jigsaw puzzle, okay? Forming a supercontinent referred to as Pangea, okay? Now, he wasn't really taken serious about his theory, simply because he could not come up with anything that would be such a mechanism to move the continents to where they are today. Now, today, it is an accepted fact, because there was a variety of different types of evidence that came out later that supported his theory. Now, one of the correlating or pieces of evidence was the fact that the rock type where the continents were once joined together, it matched. Now, the makeup of rocks, we know that rocks are made out of minerals, and certain rock formations will be in certain areas. It's almost like rocks can be used as a footprint. And then there was a correlation of fossils from the opposite shorelines of the continents that were once joined together. Now, there is a short presentation that I'm going to give to you. It's going to give you some more detailed evidence. And there's a couple of things that I'm going to issue to you as a challenge, because I know sometimes when you get data, sometimes when you get information, it's very easy to forget it, especially if you don't quite understand it. So, a couple of things I want you to be able to do at the end of my presentation, and that is be able to explain two pieces of evidence that support the theory of plate tectonics. And then part of the process that brought plate tectonics into being was the fact that there were three types of boundaries that were established. And it's my hope that at the end of this presentation, you will be able to remember those three types of boundaries and how their action contributes to plate tectonics. So let's get started. I'm going to get started by sharing my screen with you for this presentation, so bear with me. To really kind of understand how the theory of plate tectonics came about and the supporting evidence, we basically need to understand, know the structure of our planet, the planet Earth. The structure of the Earth is made up of four main layers: the crust, the mantle, the outer core, and the inner core. And I bet you guys already knew that. Now, the crust is where we live. The Earth's crust is made up of the continental crust, which is in its thickest areas could be as thick as 70 kilometers. In its thinnest area, it might be as thin as 10 kilometers. It is less dense, so it's buoyant. And that word buoyant means that it has the ability to kind of float instead of sink. It's less dense than the oceanic crust, so it's more buoyant. And it's mostly old. Now, versus the oceanic crust is thinner than the continental crust. And it's dense, so it sinks underneath the continental crust. And the evidence supports that it is young. So what is plate tectonics? If you look at a map of the world, you may notice that some of the continents could fit together like pieces of a puzzle. And that's what Wegener's proposal was brought about by. He noticed that. And if you really look close, it does look like it would fit together like a puzzle if it was drawn together. The Earth's crust is divided into 12 major plates, which are moved in various directions. This plate motion causes them to collide, pull apart, and scrape against each other. Each type of interaction is causing a characteristic set of Earth structures or tectonic features. The word tectonic refers to the deformation of the crust, deformation of the crust as a consequence of plate interaction. This is what the 12 plates look like when joined together. I want you guys to take a moment and see if you can locate the North American plate. Let me help you out a little bit. It's located right here. How about the South American plate? It's right here. Now, to move over millions of years, wow, to the point to where they are today, that's really something. And to my understanding, they're still moving a little bit, probably less than 2 centimeters a year, okay? What are tectonic plates made of? Well, if we look at this cross-section image, we can see we have the crust, but that's the part where we're on. And then underneath the crust, we have the upper mantle, the outer core, and then the very center of our planet, the inner core. And of course, we do have layers of our planet that are external, and that makes up our atmosphere. Plates are made of rigid lithosphere. The lithosphere is made up of the crust and the upper part of the mantle. So when you hear me refer to the lithosphere, those are areas that I'm referring to. Below the lithosphere, which makes up the tectonic plates, is the asthenosphere. Plate movement. Well, what Wegener didn't know is that in the mantle, there's something going on. The plates of the lithosphere are moved around by the underlying hot convection sails in the asthenosphere. Now, when we talk about a convection sail, it used to be that was something that was always referred to that happened in our atmosphere. It's the heating up and the cooling down of materials, which when they're heated up, it causes them to rise. And then when they cool down, it causes them to sink. We know that as far as weather is concerned, warm air has a tendency to be unstable and it's lighter than cooler or dense air. So in a sense, the same thing is going on in the mantle. And we know the mantle is made up of a material that we refer to as magma. And that magma, the closer it gets to the center or the outer core, the hotter it is. And when it gets hot, it begins to rise, as you see in this image. And then as it gets just underneath the lithosphere, it begins to cool off. And once it cools off, it has a movement of cycling back down. There are three types of plate boundaries, students. There's what we call the divergent, convergent, and transform. These are images that show the action that goes on with these three types of boundaries. The divergent seems to be pulling apart. The convergent, they're pushing against each other. And then the transform, it appears that they're sliding back and forth. Let's look at that in a little more detail. Divergent boundary, wow. Pulling apart, I guess you could associate that with the mathematical process of division, dividing. So they're pulling apart. While that's happening, plates are spreading apart. We call that action rifting. As plates move apart, new material is erupted to fill the gap. Now, it can happen with two ocean plates, and the result in two ocean plates interacting by being divergent boundaries, it results in what we call seafloor spreading. And this will form, or this has formed, the mid-ocean ridge. You'll learn a little bit more about that further into your virtual field trip with the rest of the teachers today. Two continental plates that are involved in this type of divergent boundary development, this will result in having volcanoes. Now, when we talk about seafloor spreading, this is where two ocean plates are diverging and they're moving apart. Molten magma erupts, forming underwater mountains under the ocean, called the mid-ocean ridge. As the ocean plates move further and further apart, new ocean floor is continuously added. This is called seafloor spreading. Here we have an image, and this image is showing different colors. Now, the blue is actually representing the older part. The red is the youngest. And as you can see, while this is happening, the red indicates there's new seafloor being added because of the opening up and magma floating to the surface and cooling off. Now, when we talk about convergent boundaries, we're talking about it coming together, pushing together, colliding. And when this happens, plates are colliding together. They may form mountains, trenches, and or volcanoes. So there we have a divergent boundary. You can expect maybe some volcanoes. And convergent boundaries, you can also expect the formation of volcanoes. Convergent boundaries, there are three types or three styles of convergent plate boundaries. Continent to continent collisions, continent to oceanic crust collisions, and ocean to ocean collisions. Continent to continent collisions may appear to be like this. It looks like this would be one that would create what? Mountainous area. The continental crust collides, one goes underneath the other. It's just all kinds of action going on. And this may, just like I said, it may form mountains, just like the European Alps or the Himalayas. Continent-ocean crust collision. In this type of collision, the continent or the oceanic crust actually goes underneath the continental crust, which, remember what we stated earlier? The continental crust, because it's less dense, has a tendency to have some buoyancy. It's a little lighter. Now, what happens here is, as this happens, it creates something called subduction. This will also form volcanoes and deep ocean trenches. Oceanic lithosphere subducts underneath the continental lithosphere. Oceanic lithosphere heats and melts, forming magma. The magma rises, forming volcanoes. Perfect example is the Andes Mountains. When two oceanic plates collide, one runs over the other, which causes it to sink into the mantle, forming a subduction zone. The subduction plate is bent downward to form a very deep depression in the ocean floor called a deep ocean trench. The world's deepest parts of the ocean are found along these trenches. Volcanoes are also formed, resulting in the formation of islands, such as the Hawaiian Islands. Now, unmanned and manned submersibles found, as they were exploring the trench, found some new species. So it made for a very interesting new ecosystem that had been exposed. And those are some creatures. Now, let's talk about the last boundary, transform boundaries. Transform boundaries form when two plates are sliding past each other, almost like two railroad trains on two tracks, one going one direction and the other coming the other direction. They're sliding past each other. What we're looking at here is a view of the San Andreas Transform Fault. That's where that type of boundary exists in the North American continent. Earthquakes frequently occur, and we've heard about all the earthquakes that have happened around this fault. The earth plates look just as you're looking right here. In fact, India, and what really shocks me, India was once an island, and now it's joined up. So there was a lot of movement because of plate tectonic. Now I've run out of time, guys, so I'm gonna stop sharing my screen right here. And listen, if any of you have any questions, I'm gonna turn it over to Dr. Gorman so he can answer those questions for you. I want you guys to have a good day the rest of the day.
Thank you, Mr. Monroe. Our student says, give a definition of plate tectonics. Plate tectonics is a scientific theory that explains how major landforms are created as a result of Earth's subterranean movements. In plate tectonics, Earth's outermost layer, or the lithosphere, made up of the crust of the upper mantle, is broken into large rocky plates. And now Ms. Schramm is going to tell you all about ocean basin formation.
Hey everybody, I'm Miss Ram and we are going to talk all about ocean basins. So let me get my little screen going. Boop, boop, boop. All right, here we go. So at the end of my little section, you'll be able to describe how plate tectonics cause formation of ocean basins. So luckily for us, Mr. Monroe taught you so much about plate tectonics. So let's talk about how that shapes our oceans. So our essential questions for today are, what is an ocean basin and what type of plate boundaries form features of ocean basins? So you've heard a little bit about that. So let's get going into the definition of ocean basin. So the oceanic basin is a land surface under an ocean that includes, continental shelf, abyssal plain, mid-ocean ridge, and other formations that may exist on the sea floor. So it's just ocean topography. So what does the floor of the ocean look like? So you can think the ocean basin is like the bottom of a bowl, right? So if our ocean was in a bowl, the bottom of the bowl is the ocean basin. All right, so like we said, it contains the continental shelf, the continental slope, continental rise, ocean floor, oceanic crust, and both continental crust. All right, so this diagram is a little more clear and it shows you the depths as well. So I like this one a little bit better. You can see the continental shelf up here. That's where the water is very shallow. Excuse me, then the continental slope as it slopes down and gets deeper and deeper. The abyssal plain, just like a plane on land, the plane is going to be flat, right? So it's flat and plain. There's not much happening. So the abyssal plain, an abyssal hill, which we won't talk about much today. Seamount, looks like a little underwater mountain. The ocean trench, and that's very, very deep, dark sea. And then in a volcanic island, and you heard a little bit about that already. So a seamount is kind of like an underwater mountain that hasn't yet reached the top, right? So I guess if it keeps going, it's going to be a volcanic island. So how are these features formed? How are the ocean basins formed? So plates can spread apart by moving away from each other, and that creates gaps where hot molten rock called magma from the Earth's mantle can rise up. When the magma seeps through the gaps, it solidifies as it cools, creating a new layer of ocean crust. So this is talking about when it creates the ocean ridge and sea spreading. So mid-ocean ridges. Mid-ocean ridges occur along the kind of plate boundary where new ocean floor is created as the plates spread apart. So sea spreading or divergent plate boundary. So divergent, of course, we know it's separating. So as those plates separate, we know that the magma from inside the Earth's mantle is able to rise up and kind of fill in the gaps. So you might think intuitively, if you're thinking about the crust separating, you might think that would be what's causing the trench because it looks like a big hole. But actually, it causes it to spread out, creating those mid-ocean ridges. So because of that, magma is hot and molten, it rises up and fills in those spots. So sea spreading or divergent plate boundary. So the plates spread apart at rates of 1 centimeter to 20 centimeters per year. So that is very, very slow moving. So those, the sea is spreading, but it takes a very long time. So 1 centimeter, 20 centimeters per year, that's like nothing. All right, so here's a diagram explaining that. So like I said, where you think those plates are diverging, it should make a hole. It actually doesn't because that magma comes up through the upper mantle and fills in the hole. So it makes it actually wider. Okay. Oh yeah, I'm sorry. The center point is also known as the mid-ocean spreading center. So the mid-ocean ridge boundaries. So you saw the plate tectonic or the plate boundaries earlier, same thing. So where the mid-ocean ridges are where those plates are moving away from each other. So you can see those outlined in white and the little white arrows showing you the direction that those plates are moving and spreading from. All right, so the next part we're going to talk about is the abyssal plain. So remember, that's the part that I said was flat, just like plains on land. The abyssal plains in the ocean are just plain and flat. So let me read the little definition I've got. So abyssal plains are the vast, flat, sediment-covered areas of the deep ocean floor. They are the flattest, most featureless areas on Earth and have a slope of less than 1 foot of elevation difference for every 1,000 feet of distance. So that is very, very flat. And you can see from even just the background that I've chosen, it's just thick layers of sediment. So it's just sand as far as the eye can see underwater. And the way you can remember that is not only because the plains are plain and boring, right? The abyssal, when you think about looking into the abyss, you're looking into nothing, right? So all you see for however long is just nothing, nothing, nothing. So the abyss. So the abyssal plains are, like we said, those large flat areas. So you can see here's the mid-Atlantic ridge. That's where that seafloor spreading is happening, that underwater mountain. And the abyssal plain is just the flat part in between. And then, of course, all the interesting stuff happens along the coast with the continental shelf, slope, and rise. And then so that's kind of the above view, and then the other kind of cut view. So you can see the abyssal plain right here. It's got all that layers of sand and sediment. All right, deep sea trenches. So deep sea trenches are actually formed at convergent boundaries. So that means they are coming together. Convergent, they are coming together. So dense lithosphere melts or slides beneath the less dense lithosphere. I don't know why I can't say that today. Dense lithosphere melts or slides beneath less dense lithosphere in a process called subduction. So you learned about that from Mr. Monroe. Subduction is going under, right? Sub. So it's going under and causing a trench. So here we've got our continental crust, and that is going over the lithosphere of the oceanic crust because it is less dense, so it's going underneath, right? Right? Yeah. Okay. Sorry, I tripped myself up there for a second. Okay. So next we have our seamount. So a seamount is an underwater mountain formed by volcanic activity. So you can see this seamount is slowly getting larger and larger and larger until it reaches the surface of the water. All right. Ooh. Okay. Hopefully I don't spoil this. Okay. So we're going to play a game. I'm going to have 4 pictures of oceanic basin features that we've learned about today. And y'all are going to guess and see if you can identify which one it is. Now, I can't hear you or see your faces, so you're just going to have to keep track of your for your own self if you've got them right. So here is our first one. So what oceanic feature do you see? And hopefully you're in your classrooms yelling out at me that you see the abyssal plain. Like I said earlier, it looks like you're looking into the abyss. That area is vast and flat and sandy. And you look and you can't see anything, no signs of life, just the abyss. All right, next one. Okay. All right, hopefully you're screaming out at me that you see the trenches. So we have a deep sea trench here. You could see that is where they are in a subduction zone causing a trench. Boop. All right, hopefully you're 2 for 2. Next one. What do you see? Hopefully you're shouting out that you see seamounts. So these are the underwater volcanic activity, and those layers and layers are building as they kind of reach towards the surface. So those are our seamounts. Whoop. All right, last one. Hopefully you're telling me that you see the mid-ocean ridge. So you can see that area is where the seafloor is spreading and being filled in with hot magma, right? So you can see it kind of steaming over there. All right. So mid-ocean ridge. And the last thing I wanted to, last 2 things, is I wanted to show you this diagram that's blank. If I had you here, I would have you label it. And I'm sure your teachers have had you label a similar diagram. So based on what we've learned today and what you know about plate tectonics, could you label this ocean basin diagram and fill in those blanks? Also, a further challenge, if you're really into building and getting creative and doing crafts, I saw some cool examples of ocean basin projects where they either carved it out of foam or built it out of paper to show those different ocean features. So I thought those were pretty cool. All right, that's all I have for you. Thank you so much, and I can't wait to see you next time.
Thank you, Ms. Schramm. We have a student who wants us to describe ocean basins formation. Any of the several vast submarine regions that collectively cover nearly 3/4 of the Earth's surface. Together, they contain the overwhelming majority of all water on the planet and have an average depth of almost 4 kilometers. That's about 2.5 miles deep. A number of major features of the basins depart from this average. For example, the mountainous ocean ridges and the deep sea trenches. And now Ms. Ramirez is going to talk about earthquakes and volcanoes.
Hello, my name is Ms. Ramirez, and we'll be learning about how plate tectonics relates to earthquakes and volcanoes. So I'm going to go ahead and share my screen with you guys, and we'll get started. I do have a couple of essential questions that I want y'all to keep in mind. So hopefully by the end of this presentation, you'll be able to answer these two questions. The first is, how are earthquakes and volcanic eruptions related? And the second is, what is the Ring of Fire? So let's go ahead and get started. Take a look at this map and think about, where do you think you will find the most earthquakes and volcanoes and why? Now, to explore this question, we're going to go to a website called Seismic Explorer. So let me get out of our PowerPoint and show you the website. And a couple of things about this website. Notice that we have our tectonic plates labeled. We also have a diagram that shows the type of plate boundary that we have. So go ahead and make your guess. Where do you think the most earthquakes and volcanoes are going to occur? And then I'll play the simulation. Before the simulation plays, though, I do want to show you guys the key. So you're going to see some colors. If it's a circle, the circles represent earthquakes and the triangles represent volcanoes. The size of the circle represents the magnitude or the intensity of the earthquake. And then the color of the triangle for the volcanoes represents how active it is. And then, of course, we have our key for our plate boundary types as well. So I'm going to go ahead and play the simulation, and you guys can observe what y'all notice. And hopefully it should shoot out right at you that most of our volcanoes and earthquakes are going to be occurring along the boundaries of those plates. And that is because along those plate boundaries, there is a lot of motion and movement. And hopefully you guys are able to notice that specifically around the Pacific plate here around the Pacific Ocean, we actually have the most volcanoes. So look at all of those orange triangles. So that is called the Ring of Fire. And we're going to talk more about the Ring of Fire when we get back into our presentation. So let me start that slideshow one more time. So this is the Ring of Fire. And the Ring of Fire is a name that's used to describe the numerous explosive volcanoes that form along the convergent plate boundary that's surrounding the Pacific Ocean. And it's characterized by numerous active volcanoes, frequent earthquakes, and again, it's all caused because of plate movement. Now, we know that about 90% of the earthquakes happen along the Ring of Fire. And again, it's because of that constant plate motion. We also know that about 75% of all active volcanoes occur along the Ring of Fire, and that's about 450 volcanoes. So the Ring of Fire is a very active region of plate movement. Now, I said the word earthquake. So an earthquake is just what happens when two blocks of earth suddenly slip past one another. The surface where they slip is called a fault or a fault plane. And we know that earthquakes happen along all plate boundaries. Now, you learned about those plate boundaries with Mr. Monroe, so here's a quick review. Along convergent boundaries, plates collide into each other, and we typically find reverse faults along convergent boundaries. We also have divergent boundaries, which is where plates pull apart or diverge. And we typically have normal faults that occur along those boundaries. The last one we have is the transform boundary. And that is simply where plates are going to slide past one another. And we typically have strike slip faults along those boundaries. So again, earthquakes can occur at all boundary types. So that's the earthquake. Now let's talk about the very cool ones, the volcanoes. So volcanoes are created due to plate movement too, and it's just a place where gas and ash or melted rock have come out of the ground. Now these can form at divergent plate boundaries and convergent plate boundaries. So remember, divergent plate boundaries are pulling apart and convergent plate boundaries are colliding. And they both occur due to the movement of tectonic plates. So they have that in common. Another thing they have in common is both are caused by the heat and energy being released from Earth's core. Now, it is important to note that earthquakes can trigger volcanic eruptions through their severe movement because of those tectonic plates, but also volcanoes can trigger earthquakes through the movement of magma within the volcano. So they can cause one another. So in our next thing, we're going to do a quick, let me get the slide to go. We're going to do a quick review of the different plate boundaries that you've already gone over with the other teachers as well. But again, feel free, teachers, to pause to give students time to kind of observe this diagram and see if they can compare and contrast the different plate boundaries. Think about where can earthquakes occur and why, and also think about where can volcanoes form or be found and why. But just remember, again, earthquakes occur at all three boundary types. Volcanoes are going to be found along divergent and convergent boundary types. So my question for you is, why are we not really going to find volcanoes along transform boundaries? So why do you think that is? And then my last thing, I have a little research activity for you guys. I would like y'all to explore the United States Geological Society Earthquake Interactive Map and their Volcano Hazards Map, and think about where is the most current earthquake closest to you, and also where is the closest volcano to you. So let me show you these two websites really quick. The first one is the USGS earthquake one, and you can explore this website and see where there are earthquakes currently happening. So if it's red, that means it occurred within the last hour, and if it's orange, it occurred within the last day. So you can already see that we've actually had a couple of earthquakes here in Texas within the last day. So I thought that was pretty interesting, but feel free to look through this website to see where an earthquake occurred near you. The other one is for volcanoes. It also shows the earthquakes too. So the earthquakes are going to be the circles, the volcanoes are going to be the triangles, and you can actually see, I think this is a more updated one. So in Texas, we've actually had some earthquakes that have occurred even within the last 2 hours. So apparently there was an earthquake in or near Garden City, Texas, and that was just happening today. So that's pretty interesting. So you guys can look through this website and figure out where the closest volcano is and where the most recent earthquake is that's located near you. So that's all I have for you guys today on volcanoes and earthquakes and how they relate to plate tectonics. We're going to give it back to Dr. Worman to answer any questions.
Thank you, Ms. Ramirez. And a student wants to know just what you were talking about. When is the latest fairly large earthquake in Texas? An earthquake of a magnitude of 4.5 struck near Stanton in West Texas on Monday. This quake struck at a depth of 7.8 kilometers. That's 4.8 miles. And the next part of the question was, have you ever been in an earthquake? And yes, I lived in California for quite a while, and they have them they have earthquakes out there all the time. And a lot of them are up between 4 and 5 range on the scale. Thank you again, Ms. Ramirez. Now, Mr. Dominguez is going to talk to us about mountain building.
Hey guys, in this portion of your virtual field trip, we are going to be talking about mountains and how they are formed. And even though we don't have mountains in this region of Texas, we are currently standing on the same material that gives rise to mountains. Even this sedimentary rock comes from that same material. And what am I talking about? Well, I'm talking about the Earth's crust. And as you learned earlier, the crust is not one giant piece. It's actually composed of several plates. And when those plates crash into each other, because remember, they're not static, they're moving right now. When they crash into each other, they form mountains. But I will give you guys a better visual inside. So let's get this presentation started. It's kind of cold out here. So let's go back inside. All right, guys, so let's quickly go over the type of boundary that makes mountains possible, and that's the convergent plate boundaries. And that just means that they are crashing into each other. So the lithosphere, and here's the asthenosphere. And just so you know, this asthenosphere facilitates the movement of our plates. So this is a very fluid portion of the Earth's crust, which facilitates the movement of the plates. So it makes plate tectonics possible. But we are concerned with the convergence of these two plates. So when two plates collide, so as you can see, what's happening here, one plate is actually sinking, which is called subduction. However, in the process of doing so, it creates a rise in the Earth's crust, which we know as mountains. So to better visualize this, we're going to do a little demonstration in a second, but just know that it is convergent plate boundaries that form mountains. There are other types of boundaries. So we have divergent plate boundaries and transform plate boundaries, and they're all interesting in their own way, but we are concerned in this section with the convergent plate boundary. Some of the highest peaks on Earth were created by convergent plate boundaries. What you guys are looking at is the Himalayan mountain range that sits between the Tibetan Plateau and the Indian subcontinent. The Himalayan mountain range was created millions of years ago when the Eurasian plate and the Indian plate came crashing into each other. You guys might be familiar with one of its highest peaks, Mount Everest. Mount Everest has an altitude of around 29,000 feet. That is an incredibly tall mountain. Many people have attempted to climb Mount Everest, and once upon a time, only a few could claim that they had done so. However, to this day, around 5,000 successful climbs have been recorded. In this animation, you see what occurred millions of years ago to form the Himalayas. As you can see, the Indian plate is converging towards the Eurasian plate. And as they crash into each other, they form what we now know as the Himalayan mountain range. However, this process would not take seconds. It would take millions and millions of years. And as you can see here, we have the beautiful peaks of the Himalayan mountain range. All right, guys, so what we're going to do is we're going to recreate the process of mountain formation. Now that we know a little bit more about those convergent boundaries and how those plates are crashing into each other, let's see if we can use some towels to better visualize that process. So what I'm going to do is I'm going to stack some towels, and these are different colors just so we can better see those rock layers. And remember, this process is constantly happening. So let's pretend that this is the Eurasian plate and this is the Indian plate. And those plates are actually crashing as we speak. That's why Mount Everest continues to grow to this day. In fact, it grows a few millimeters every single year. So these convergent plates are crashing into each other. And this process takes millions and millions of years, but we're going to fast forward here. So let's see if we can get a mountain. There we go. So this is a very simple way to visualize what is happening when two convergent plates crash into each other, okay? So simple physics tells us that we are going to get a rise in the Earth's crust. If you guys want to check out mountains that are closer to home, you could head on over to West Texas to Guadalupe Mountains National Park. There you will find Guadalupe Peak, which is the highest peak in Texas. What's really wonderful about this area is that it was once underwater. So most of what you will see is old coral reef. For those of you that don't know, Texas was underwater about 250 million years ago. However, these mountains were formed in the same manner that we talked about earlier. So guys, I hope that you enjoyed this portion of your virtual field trip and learned a little bit something about mountain formation. I hope to see you guys next time. Have a wonderful rest of your day.
Thank you. Describe mountain building. In ocean-continent collision zones, faulting and faulting of rocks combined with volcanism to build mountains. An example of mountains built this way is the Sahara Nevada mountain range in Utah and Nevada. that was formed about 140 million years ago. And now I am going to share the screen. Plate tectonics. During this virtual field trip, students explored plate tectonics. Students identified the major tectonic plates, described how plate tectonics causes major geological events such as ocean basin formation, earthquakes, volcanic eruptions, and mountain building. Mr. Monroe told you about plate tectonics, ocean basin formation by Ms. Ram, earthquakes and volcanic eruptions covered by Ms. Ramirez, and mountain building by Mr. Dominguez. Thank you so much for joining us today. Teachers, if you would, go to www.tiny.cc/6-8 feedback, fill out a very short form and send it back to us. We would certainly appreciate it. You guys have a great rest of the day. More importantly, have a great rest of your life.